When an app icon expands on an iPhone, the pixels move with a specific sense of weight and momentum. Most applications rely on linear motion, where an object travels from point A to point B at a fixed, unchanging speed. This creates a robotic effect that the human eye perceives as unnatural. Apple avoids this by using a system architecture that simulates real-world physics. Their engineers calculate how an object with mass would actually react to tension and friction. We are going to use Xcode to build this exact spring animation in SwiftUI, and we'll do it in under 5 minutes. Mastering these physical simulations allows you to build interfaces that feel intuitive and responsive to the user's touch. You will need a Mac with Xcode installed and a basic understanding of how to manage state in SwiftUI. Start by creating a standard glassmorphic card view. We want this card to expand in size whenever the user taps it. To animate that expansion, apply a basic linear animation modifier to the card view. Because the animation is linear, the velocity is a flat line, moving at constant speed. This creates a jarring transition, ending in a sudden dead stop. Physical objects need time to gain and lose momentum. Ignoring this creates a programmed imitation, not a real interaction. Linear motion fails in UI design because it detaches the interface from the physical laws of the world around us. To fix this, remove the linear modifier and replace it with the default spring command. The card now behaves like it's attached to a rubber band. It accelerates, overshoots, and smoothly oscillates into place. In the background, SwiftUI calculates tension and elasticity. You are no longer moving pixels. You are defining the stiffness of a virtual spring. This default spring is a significant improvement over linear motion, but it is often too bouncy for a professional production app. Moving from a generic bounce to a high-end interface requires us to carefully calibrate these physical forces manually. We can control the feel of the animation by adjusting the mass variable, tweaking the stiffness setting, and fine-tuning the damping. Inside the spring modifier, we will set a response time of 0.4 and a damping fraction of 0.6. Beginners often make the mistake of setting the friction, or damping, too low. The damping fraction determines how quickly the system loses energy. Without enough damping, the UI continuously shakes, looking cartoonish. By setting damping to 0.6, the motion curve forms a smooth arc that tapers off quickly, bringing the card to a controlled rest. This balance of forces creates a movement that feels grounded in reality while remaining fast enough for a touch interface. When we compare the original linear motion to our calibrated spring, the difference in quality is clear. One feels like a programmed script, the other feels like a physical object settling into place. You can apply these same parameters to navigation transitions, drag gestures, and menu reveals to give your entire project a consistent, tactile feel. By replacing fixed coordinates with physical math, the interface begins to respond to the user the same way an object would in the real world.